In this video, we're going to take what we learned in the last one about hybridization and use that to kind of get to our end goal of learning about hybridization, which is really to help us determine what do molecules actually look like in 3 dimensions. So we're going to be determining what's known as the molecular geometry, which is how we describe the shape of a molecule in 3 dimensions. So the molecular geometry of something is determined both by the number of electron domains, aka the hybridization, essentially, and how many of those electron domains are lone pairs versus bonds. So the total number matters, and then how many of that total is lone pairs and bonds matters as well. So we know how to determine the number of electron domains. We label that total number of electron domains as the hybridization of the central atom. So that's kind of step 1 in the process. And then if we look at how many of those electron domains are lone pairs versus bonds, we find a specific label for each combination. That is what is known as the molecular geometry. So essentially, what is happening when a molecule takes its 3-dimensional shape is that the electron pairs, the electron domains, all contain electrons. As their name suggests, electrons are all negatively charged, and like charges are going to repel one another. So the electron domains all repel one another, which means that they are going to spread out as much as possible around the central atom in 3 dimensions. And that 3D thinking is really the hardest part. It's easy to kind of think about what it would look like if we drew it on paper, but when we're drawing a structure flat, we're not necessarily accurately representing what it really looks like if you could hold it in your hand, if you could hold an actual model in your hand. So this idea of the electron domains repelling one another is known as Vsepr Theory, commonly pronounced as Vsepr, although that's not really how it's spelled. Vsepr Theory is what everybody calls this, which stands for valence shell electron pair repulsion. Which taken as one big long phrase sounds a little bit intimidating, but if we break it down, electron pair repulsion is what we were just talking about, that our different electron domains all contain electrons. Electrons are all negatively charged, so they're going to be repelling one another. And the valence shell is what is generally responsible for bonding, is those outermost electrons in your atom are the ones pretty literally on the surface of your atom if you're imagining it as a sphere. So those are the ones that are going to interact with other atoms most easily. So it is the electrons in the valence shell that are repelling one another, and that is what is responsible for the shapes that we actually observe for molecules. Reminder, that Lewis structures that we've been drawing are not intended to convey any amount of three-dimensional structure. They only show how things are connected. They only show us the connectivity of an atom, where are the bonds, where are the lone pairs, but they don't actually give us any information about what it looks like in 3 dimensions. For that, we need to take our Lewis structure and apply this understanding of Vsepr theory that my electrons are going to spread out as much as possible, and we get a whole collection of shapes. So you will receive this as a handout, so you don't need to copy all of this down. It is already posted on Google Classroom, and you'll get a paper copy in class if you haven't already. So this shows us our different combinations of how many electron domains each of these different shapes has, and how many lone pairs on the central atom each of these shapes has. So it's constructed as a table, so we can easily kind of match things up. If we identify that we have an sp2 hybridized central atom with no lone pairs on it, that means it's going to have what we call a trigonal planar geometry. So these little pictures are trying to show you what these molecules actually look like. Note that the names are trying to describe the shape that the molecule makes, specifically the shape that the bonding atoms make. So in the case of a linear molecule, it is talking about all 3 of my atoms are creating a straight line. In the case of trigonal planar, all of my atoms lie in the same plane, is what the planar part of that means. Trigonal meaning my peripheral atoms point to the corners of a triangle. For the bent molecule, the atoms are creating this sort of bend, this kind of V shape. Note that these sort of bubbly bits are the lone pairs, so the name of the geometry is kind of ignoring the lone pairs. It's describing what shapes do the atoms make. So trying to familiarize yourself with what these things actually look like is going to be really important in our next lesson. So you want to make sure you're not focusing just on what is it called, but you need to have some understanding of what does it look like. So I think trying to figure out how each of these names is related to the actual shape can be really useful. Some of them are a little bit easier to see than others. This version of the bent geometry is a little bit harder to see, but you do have that same V shape over here. They just stuck one of the lone pairs in front, which is inconvenient, but was the picture I had available. So some of the other ones are a little bit less obvious. A lot of them are describing the shape, the like 3-dimensional shape that the atoms make as a whole. So for instance, the trigonal pyramid here, if you imagine connecting these 3 atoms and like enclosing that whole space that those 4 atoms make together, you have a pyramid and the base is a triangle. So the trigonal pyramid is the shape that that is making. So you can kind of go through these more on your own to think about how these relate. Some of them, again, are pretty obvious. T-shaped literally makes a T. We've got a couple other versions of linear in different places. So basically we're just looking to be able to match up the hybridization and the structure of the molecule with one of these different geometries. So you also have a sort of condensed version of this table without the pictures on the back of your periodic table. So with all of the assorted information, the polyatomic ions that you've been using in that same area, you will find this version of the chart that has the same hybridizations down the left and number of lone pairs across the top, with just the names to help you remember how things line up. So you will have this version available to you on quizzes and tests, but the kind of visualization of the actual structure is going to be important as well. So let's look at a few examples. So here are a few different structures, and based on these structures, we're going to be able to determine our molecular geometry. So the first thing we want to identify is how many electron domains are around our central atom, aka what is its hybridization. So for the first one, we have a double bond on one side and a double bond on the other. So that is 2 electron domains. And none of them are lone pairs. So if we apply this, 2 electron domains is sp hybridization, 0 lone pairs is going to put us in this column. That gets us a molecular geometry known as linear, meaning that those 3 atoms all lie in a straight line. So that means that in this particular case, our Lewis structure that we happen to draw this way is actually pretty accurate. That's more or less what the molecule looks like. If we look at this in 3 dimensions, we see that my molecules all, or my atoms rather, all lie in a perfectly straight line. The angle between them is 180 degrees because that is as far apart as 2 things can get. So when we're considering what our shape looks like, we're really thinking about like how far away can I put, or how far apart can I put this number of things. My electron domains want to get the heck away from each other as much as they possibly can. So for 2 electron domains, that is going to be on opposite sides of the molecule, which is what gives rise to this 180 degree bond angle that we see here. So why don't you pause here and give the rest of these examples a try on your own using the same principles. So next up, we'll go to the top right. We have SF4. On our sulfur atom, we have 4 bonds plus 1 lone pair. So that is a total of 5 electron domains, one of which is a lone pair. So 5 electron domains is the sp3d hybridization. 1 lone pair puts us at the seesaw geometry. So our molecular geometry for this one is called seesaw. And if we look at this one, there it is, in 3 dimensions. Our lone pair is currently not shown. If I turn it on, that sticks the lone pair over there. So our lone pair is in this region over here. But we can see that this molecule is not flat. It does not really look like how we drew it. So we drew it, or I drew it, I guess, kind of looking at it from more or less this angle, where we had my fluorine atoms just kind of up, down, left, and right. On paper, the way I drew the Lewis structure, it sure as heck looks like a 90-degree bond angle between everything, but in our actual structure, we can see that that's not true. So these ones, from sort of this one to this one, is about 90 degrees, and from that one to this one is about 90 degrees, but in between these two is not a 90-degree angle. That's actually about a 120-degree angle. So we have different angles in 3 dimensions, a different shape in 3 dimensions that is not easy to convey in a 2-dimensional drawing, in a 2-dimensional Lewis structure. Next up, we have IF3. We've got, oopsies, 2 lone pairs plus 3 bonds. So once again, we have a total of 5 electron domains, or sp3d hybrid, but this time we have 2 lone pairs. So when we go to identify the geometry of this one, we're going to be in the same row, moving over a column, and that gets us the T-shape. So in this particular instance, I chose to draw my Lewis structure with my peripheral atoms kind of evenly distributed around my Lewis structure, but we find in the actual structure that that is not the case, that it pretty much makes a T-shape, hence the name. It looks an awful lot like the letter T, that I do not have an equal distribution of my fluorine atoms around the iodine. They create this sort of shape instead, and that is because of those 2 lone pairs. When you consider all of the electron domains together, we have a pretty even distribution of electrons, but they don't all have atoms connected to it. So the geometry we're considering is just really the shape that the atoms make, so we call it a T-shape. Should write that down. Molecular geometry, T-shaped. And then last but not least, OF2, we have 2 bonds plus 2 lone pairs for a total of 4 electron domains, 2 of which are lone pairs. So when we come up to our molecular geometry chart, 4 electron domains is sp3 hybrid, 2 lone pairs puts us at the bent geometry. And when we look at this guy in 3 dimensions, we see that it does create that kind of V shape. Looking at where our lone pairs are placed, we see that we have a fairly equal distribution around our central atom. But just the atoms themselves create this bend, hence the name bent. So just based off of the Lewis structure, we can identify what the molecular geometry is likely to look like, but it's really, really important to distinguish between what the Lewis structure makes it seem like the geometry is. I drew this as though it were linear. That's perfectly fine because Lewis structures are not intended to convey the actual shape. But you have to keep in mind that this isn't actually a straight line the way the molecule really exists, and that's going to be very important for our next lesson.